Hi everyone, in this video we're going to work through an application that involves a polynomial function. So the idea for these would just be that you can get a rough sketch of this graph and then you can figure out what that's telling you about the situation. So here we have a function that inputs the velocity, what is this? The velocity of the stream. The velocity of a water wheel. So we have a water wheel going round and round and round in a stream that's going 4.1 feet per second. And if we input the velocity of the wheel, this function will output the amount of power that's generated. Okay, so let's see. I'm going to say that we don't want to see negative velocity of the wheel. Negative velocity does have some meaning. It means going the other direction, but I'm guessing the shape we get probably won't make sense in that context. We can change our mind if we want to. So this thing is already in a factored form, which means I can rewrite off 16v equals 0 when v equals 0. So this is my v, sorry for the crooked axis. And 4.1 minus v squared equals 0 when v equals 4.1. Okay, so let's see. Global behavior, we would have a 1600v multiplied by a negative v and another negative v. So that actually ends up positive since there are two of these. Positive 1600v cubed. So a right side up v cubed would start from negative infinity. This is a multiplicity 1, so we cross right through at 0. And then 4.1, that one has a multiplicity 2, so we would bounce off at 4.1. And continue on. Okay, so part of the directions here are we're only really supposed to sketch over a reasonable domain, so I think we want to make some judgment calls. And I just want to take this chance again to say I'm not expecting you to be experts about power or water wheels or anything, but I think it's fair to say that we don't want to see this. We're going the other direction. We're getting negative power. And then on this direction, I think at minimum you should cut it off at 4.1. I actually think there's a decent argument for estimating where this maximum is and then cutting it off. What I'm seeing here is as the speed of the wheel gets closer to the speed of the water, first our power increases and then it starts decreasing again, and it says we're not getting any power if the wheel is going at exactly the speed of the stream. And then after that, all of a sudden we start to get, if it's going faster than the stream, more and more and more power. I don't think the wheel should in general be going faster than the stream. The stream is what's supposed to be turning it, so we should definitely cut this off. Again, I think probably our best bet would be to estimate where this is and cut it off. I'm thinking that what happens is as the wheel goes faster, it hits some point where you're getting maximum power, and then as it speeds up from there, you're just not getting more power instead of getting less power. Doesn't seem to make sense, but I would take anything between the maximum and the 4.1. Any of that would be fine. I don't need you to be experts on power or water wheels. If you don't think I'm quite going to get what you were thinking, just write me a little note about why you chose where you chose to cut it off. That's fine. So you want to look for the really big glaring problems and make sure you leave those out. We'll get at trying to figure out where this is in just a minute, so that's coming up. I'm just going to save it for part C. Okay, so we want to find and interpret any intercepts of the graph. So we get 1 at 0, 0, and 1 at 4.10. And again, if you think this is outside of reasonable domain, then I guess you're off the hook on that one. But just to be safe, we'll say what both of those are trying to tell us, whether or not it's reasonable. 0, 0 is saying if the velocity of the wheel is 0, there's no power generated. So if the wheel isn't turning, we aren't generating power, which seems reasonable. And then this one, which seems a little more questionable, is telling me, so this is 4.10, it's telling me that if the wheel is, the velocity of the wheel is 4.1 feet per second, which is exactly the velocity of the stream. So if the wheel is spinning at the exact velocity of the stream, we're not generating any power. So that's what it's saying. I'm not claiming that that necessarily is reasonable. Seems a little weird, but that's what it's saying. Okay, the last part on this one is to estimate the velocity that results in the maximum amount of power being generated. So ideally, you will have a graphing calculator for this. This is why they're recommended. If not, you can do a little bit of guess and check on your own. If you have a table, that'll be a decent substitute. So I'm going to go ahead and put this in 1600. We don't get a v, so we'll just make it x. Times 4.1 minus x squared. Oh, need a parenthesis, squared. Oh my goodness, hold on. Maybe I will get this parenthesis where I want it eventually. I don't promise. There we go. Parenthesis square. Okay. Window. So I'm going to go ahead and say we want to see everything. We'll just go from 0 to 4.1 for x's. So if you know a good interval for your x values, again, you can just use zoom fit to get a good interval for your y values. It'll find any tops or bottoms for you. Okay, so there's the little piece we were seeing. We want to estimate the top, and actually if you use zoom fit, you probably already have a decent estimate in here. If you just go back and hit your window, you're seeing this y max is 16,335. You can also hit trace and just kind of arrow around. Notice again 0 and 4.1, so 2.05 would be in the middle, and the maximum is definitely before. In fact, it seems well before we get there. So 16, 267, 314. Okay, so we hit a max somewhere in there, 16,335. If you want to remember a couple of keystrokes, there's a way to get your calculator to do this without the guess and check. You would hit second and then trace to bring up the calculate menu, C-A-L-C. And then we're trying to find a maximum. So you want to arrow down to number 4. You need to give it a left bound and a right bound. So you need to arrow over or type in an x value that you know is to the left of the maximum, and hit enter. Arrow over, if you want to do bigger jumps, hit second and over, it'll make bigger jumps until you're sure you're on the right side. And then I don't know why it asked for a guess. I guess if you had more than one local maximum, it'll find the one closest to your guess, but we only have one. So just hit enter again. And there it is. So this one with a little less rounding error tells me that my maximum happens actually over here at 1.3. 16,336.8. So let's look at what the questions he was actually asking. This said, estimate the velocity to the nearest tenth of a foot per second that results in the maximum amount of power being generated. So velocity of 1.3, what were my units here? Feet per second. So if you don't have a graphing calculator, you're just going to have to go with whatever calculator you have, and you're going to have to do a little trial and error. We know it's somewhere between 0 and 4.1, so you could start plugging in. You can plug in 1 and 2 and 3 and narrow it down to between 1 and 2, and then you can start plugging in tenths. So plug in 1.5, 1.6, 1.4, and keep going until you see that you're hitting that peak. Or if you have a table, you can scroll through your table and it should give you a good idea as well. So you have a little bit more tedious process if you don't have a graphing calculator. All right, that's it for that one. Thank you for watching.